so we have this optimization problem for calculus. This is what the question is asking us to do. We have an open box of maximum volume that is to be made from a square piece of material, 18 inches on the side, and by cutting equal squares from the corners and turning up the sides. Using calculus, find the height of the box and its exact volume. So I just drew this out to show what we're dealing with. We have this square piece and we have these corners that are cut out. So I labeled these x and x because our x will equal our height. So then I did 18 minus 2x and 18 minus 2x here also, so to represent our length and width. So being that we're dealing with volume, we have to use the equation for volume, which is volume is equal to length times width times height. So what I did was I substituted this, the things I had set up over here, which will have give us an equation where we have the volume is equal to 18 minus 2x times 18 minus 2x times x. So there's our length times width times height. So all we have to do is just simplify things down. I pulled out a 2 from each of these. So what results is you have 2 times 2, which is 4. So that gets factored out to the outside. It's a little confusing. You just have to look over it. So I factor that out. And what we do next is we just multiply these all out. Just do your foiling. And we end up with 4 times 81 minus 18x plus x squared times x. So after this, we distribute this x through what's in these parentheses. So we end up with 4 times 81x minus 18x squared plus x cubed. So that's after simplifying everything down. I have not taken the derivative yet. So here is where I take the first derivative. This remains on the outside. What ends up happening is we're just left with this 81 minus 36x plus 3x squared. And we can further factor this down if you just look at you just want to get a common factor going here. So we have 4 times 9 minus x times 9 minus 3x. And if you FOIL this all out, you'll get back to this same thing here. So now we have to set the first derivative equal to 0. What results on this side is we get x equals 9, which we cannot use because if I plug it back into the side here, I'll get 18 minus 2 times 9, which results in 0, which means we can't use it. So that leaves us with this x equals 9 over 3, which is equal to 3, which we can use. So what I'll do now is I'll plug this 3 back into our original function, our original equation. It's not the first derivative, it's just the thing that resulted after we simplified it down a little bit. So I have v of 3 is equal to 4, then parentheses 9 minus 3, parentheses, and then another parentheses 9 minus 3 times 3. So I just plugged it in for x right here after I had just simplified it down. So what we'll get is 4 times 6 times 6 times 3. And this will actually give us the volume of this box with the open top on it. And it will be 432 cubic inches. And you always have to remember to put your units, or you possibly could get a mark down on an exam or a quiz, whatever you're doing. So now the last thing we have to do is see if this is truly a max. So what I did was I took v prime and the v prime, and which is 4 times 81 minus 36x plus 3x squared, and I took the second derivative, and what I was left with was 4 times negative 36 plus 6x. And I did the second derivative with plugging in 3 for x, so we get 4 times negative 36 plus 6 times 3, which results in negative 72, which is less than 0, so that means we have a relative max because it's concave down, so we know this is the maximum volume for this box with the open top, which is 432 cubic inches.